Okay, welcome to a homework video where we'll work through Mechanics of Materials, problem 12, 101. I'm going to try this in OneNote so we get a little bit more room. I'm not going to have to jump back and forth between slides and whatnot. Let me just change the pen here a little bit. Alright, so we've got problem 12, 101. We have this beam pinned on one side, roller here, roller there, and then 2 point loads, and we're looking for the reactions at the supports A and B, and to draw the shear and moment diagrams. And we're told that EI is constant, which means that we have the same cross section that makes I constant, and E, same material is constant, so we're in good shape there. So what do we have? What's our approach going to be here? So step 1, we need the elastic curve. Step 2, we'll draw a free body diagram. 3, we'll select a redundant. 4, we'll do some integration. We'll have redundants and then our boundary conditions. We'll solve using our boundary conditions and continuity. Oop, got a little crazy. And then step 6, we'll draw shear and bending. So that's the approach we're going to take. Looking at our diagram here, what do we have? Well, we have a pin here, so we know that y is 0 over here. Y or v, if you're looking at the book, our deflection is going to be 0. Same thing at this point here, and at this point here. So those are our boundary conditions. Looking at this again, we see that this is symmetric, right? At L over 2, we have this load, another L over 2 from the other side. We have this load. This thing is right in the middle as well. So our elastic curve is going to be something like that. It should be symmetric, but not quite. So what does that tell us? Well, at the center here, since it's symmetric, our slope is also going to be 0. That's our continuity equation here. So we have 3 boundary conditions, 1 continuity equation. What are we going to have here? We have first degree indeterminacy. Right? We have 1, 2, 3, 4 reactions. Right? So we get 2 here, 1 here, 1 here. So we get 4. Oh, it must be on top of that. 4 reactions. We get 3 equations of equilibrium. So we're first degree. And we also have, we're going to have a couple integrations here, right? So we should be able to solve this this problem. So we're in good shape. Let's draw our free body diagram. So I'm going to try to kind of keep this right on top of the other one, or right below it, excuse me. So we're going to have AY, AX, P here, BY there, P here, CY over here. And these are all L over 2 away from each other. This is L, L, L over 2. Alright, so there we go. We've got that. Excuse me. Alright, so what do we have going on? Well, let's see. We're going to take some, we're going to use our equations of equilibrium and our deflection piece. So our support reactions using equations of equilibrium. Start with the easy one. So the sum of the forces in X is 0. AX. So we've got that reaction done. We use one of our equations of equilibrium. Sum of the forces in Y. So what do we have there? We have negative P. We get negative 2P plus AY plus BY plus cy, so we can't solve anything directly there. And now if we do our moments around A, those have to add up to be 0. So I get, from this applied force, we get P times L over 2, and that's going to give us a negative moment. So negative P times L over 2. Away from that, we get L acting at By is acting at L, and that's a positive moment. We'll be rotating counterclockwise. Then we get negative 3L over 2 times P for this guy here. Right? He's L over 2, L over 2, L over 2, so 3L over 2, negative, and then plus 2L times Cy for this guy. So we've got those two. And then just for simplification or further reflection later, recall, I'm going to call this one equation 1. This one I'm going to call equation 2. So we can refer back to those equations. Right? Now I'm going to draw a couple sections of this diagram. So I'm going to take one section that will be from this end over somewhere intermediate between Cy and our load P, and then I'll do another one that includes load P all the way to the end, and that'll be segment 2. So looking at those, segment 1, we have this guy, we have Cy acting here, our shear is going to be up, our normal this way, but it's going to be 0, and our bending moment is over that way. We're going to call this coordinate from the right x1. And for the other segment, now we've got a little bit longer of a thing. I have P acting at L over 2, Cy still have a normal shear, and our bending moment. And we're going to call this x2. Alright. And so the distance from here to there is going to be x2 minus L over 2. Right? So x2 is all the way to the end, L over 2 gets us to P, so this is that distance between those two. Alright, so using those, so there are moments from this guy. So function of x1 is going to be, what do we have? We don't get any moment on this side, so we just get moment, right, from this guy. It has to equal, sorry, let me get rid of that for a second. So if I'm taking the moments around this point, this value here is our moment. We have Cy times x1 is going to equal, and then I have my moment there. And then this guy would be plus, am I going the right way? That's clockwise, so it's going to be negative, sorry. Negative m, so m of x1 equals Cy times x1. Alright, so we've got that. And then from this one here, what do we get? My moments around. So using that, I'm going to get Cy times x2, this whole length, minus P times x2 minus L over 2 times this part, minus m as a function of x2, this value there. So as I rearrange that, m as a function of x2, Cy x2 minus P times x2 plus PL over 2 as I multiply those two together. Alright, so I've got those two pieces. And one thing to note here is we'd expect to see the same thing on either side, right? If I started on this side or that side, I'd get the same equations here. I just picked the right side. So now if we go on to our, using our slope and our elastic curve, we can do our equations here. We know that the EI times the second of y with respect to x is going to be our moment as a function of x. All right, so filling those in, cy x1 equals EI dx squared. Do an integration on that guy. So I get E, just pulling this over to the left side, dy dx equals cy x1 squared over 2 plus c1. Integrate a second time. So I get cy x1 cubed over 6 plus c1 x1 plus c2. I'm going to call this one equation 3, equation 4 here. Alright, so we got those guys. Now if we move on to the next one for the other piece. So I have from this equation, so I have cy x2 minus px2 plus pl over 2 equals ei second of y with respect to x. So first integration, ei dy dx cy x2 squared over 2 minus px2 squared over 2 plus pl x2 over 2 plus c3. So we had c1 and c2 up here. Got a third one here now. So it's going to be equation 5. Alright, just verifying I've got the correct thing. Okay, good. And then a second integration. So you have cy x squared x2 to the third over 6 minus px2 to the third over 6 plus plx2 to the second over 4 plus c3x2 plus c4. That gets us equation 6. Alright, so now that we've got these crazy things, where do we go from here? What are our boundary conditions? we call them up here, right? We work our way back up. Right, so we had these boundary conditions. We had y equals 0 at x is, well, this would be x2 is at 2l. At x2 equals L, we have y equals 0, and as x2 or x1 is 0, y is 0, and at L we have the slope is 0. So those are going to be our boundary conditions. Actually, this one is called the continuity equation or condition. So we're going to fill those in. Where are we going to fill those guys in? So we have y equals 0 at x1 equals 0, y equals 0 at x2 equals L, and dy dx equals 0 at x2 equals L. Alright. So using equation 5 here, we're going to pull in this value at x equals L. We have ei times dy dx is 0. That's going to go to 0. Zero equals, let me just fill that in here, dy dx is 0. 0 equals cyl squared over 2 minus pl2 squared over 2 plus pl times l over 2 plus C3. These are 2's, sorry, they kind of look like L's. So we get negative PL squared over 2 plus PL squared over 2. These two go away. So we find that C3 is negative CYL squared over 2. It's one of our constants of integration. So there we go. Also using now from equation 6. At x2 equals L, we have, oh, sorry, not D, y equals 0. So filling in this guy, y is 0 on the left-hand side, so we get CYL cubed over 6 minus PL cubed over 6 plus PL squared over 4 plus C3L plus C4. And we remember now that C3 is up here. So we have 0 equals CYL cubed over 6 minus PL cubed over 6 plus PL cubed over 4 minus CYL squared over 2 times L. Filling that in, multiplying by L plus C4. Alright, so what do we get here? This is a negative CYL cubed over 2. This is a CYL cubed over 6. So as we carry that through, what did I miss here? CYL to the 4th. Yep, that's there. Good, good. Alright, I think I'm set. So as we arrange these guys, we get negative 2/12 positive 1/12, right? CYL cubed over 6, CYL cubed over 2. So we solve that, we find that C4 is CYL cubed over 3 minus PL cubed over 12. Right, so we had that 1/12 here. It's on the same side as that, so it becomes negative. So I simplify that fraction, I get CYL cubed over 3. And so there we are. That's our second equation. All right, now we're going to use equations 4 and 6 again. At x1 is the same as x2 equals L over 2. These two equations have to line up, right? I shouldn't get a different answer for my displacement when I'm at L over 2 with this or L over 2 with that. So these should line up. So I'm going to use equation 4 or equation 6 for this, right? So my displacement here. So what do I have for that? So using equation 4, my equation 4 was EI y as a function of x1 is CY over 6 x1 cubed plus C1 x1 plus C2. And we don't have either of those values, right? We do have, from equation 6, we had EI, function of x1, EI y as a function of x2, excuse me, is CY over 6x2 cubed minus P over 6x2 cubed plus PL over 4x2 squared plus C3 x2 plus C4. We have C4 and C3 from up here, right? So there's C4. We'll plug that into here. Here's C3 from back up here. So I've got those values. I don't need to solve C1 or C2. In that case, I can find Cy in terms of P at this point. All right, so let's move through that. And these two have to be equal to each other, so I can set this one equal to that one at the same point here. So I get L over 2 is my value here. Oh, this is the other piece of my elastic curve here. So as I look at this at L over 2, I would expect this to be symmetric as well. Or my slope has to be the same regardless of which direction I come from that. Sorry, I jumped a little bit ahead there. From equation 3, this be equal to equation 4 at x1 equals x2 is L over 2. So going back to that equation, what do we have? So dy dx is from x1 is cy x1 squared plus over 2 plus c1. And the other equation is going to be from this guy, cy x, so this will get me c1. So what do we have? So we had cy over 2 times L over 2 squared plus c1 equals cy over 2 times L over 2 squared minus P over 2 times L over 2 squared plus PL over 2 L over 2 minus CY L over 2 L squared over 2. So as I look at this guy, I'm trying to solve for C1 here. C4 I had from up here. So let's expand this out a little bit. Excuse me. So we get cy L to the 4 L squared, excuse me, over 2 times 4, 8 plus C1 equals C4. C4 was cy L cubed over 3. So we multiply by 1/2 from here times L squared over 4. Oh, sorry, I'm jumping ahead. So it was L. Alright, so that's L cubed over. So that is C part of C4. Get rid of that. Minus PL cubed over 12. All of that over 1/2. Yes. Okay. And then this is 12 times L squared over 4 minus P over 8 PL squared over 8 plus PL squared over 4 minus CYL squared over 2. Alright, what do we get there? So we have some terms we need to expand out here again. So we have CYL cubed times 3 over 3, 6, 24. And that's, make that a 5, because multiplied by L over 2. Minus PL to the 5th over 12 times 2, 24, 96 minus PL squared over 8 plus PL squared over 4 minus CYL squared over 2. So let's see, we've got PL to the 5th. Oh, and this is on the other side we had CYL squared over 8 plus C1. CYL squared over 2. Okay, so these are not going to cancel, but these are the same. These two are the same types, right? CYL squared. And we have CYL to the 5th. So there's an L to the 5th here. We could collapse those two together. These two are the same on top here. So as we do this, did I lose something? How did I get rid of that? C3. Oh, this is CY. Oh, I subbed the wrong thing in there, right? It's supposed to be CY, not CL. C4. Goodness gracious. So I screwed this up here. That term is wrong. What that should be is CYL squared over 8. There we go. So as I subtract this term from that, that one's going to collapse with this one and this one. So we find then, okay, that simplifies things up quite a bit. C1 works out to be PL squared over 8 minus CYL squared over 2. Alright, so we've got 3 of our constants done. C1, C3, C4. Alright, and then also at that same point, our deflection has to be the same, so I can set those equal to each other. So we can say that equation, sorry, this was not equation 3 equals equation 4, that should be equation 5. Equation 4 equals equation 6. Y equals y2 at x1, x2 equals L over 2. So same point where that load P is applied. So now we're going up to equations 4 and 6. So this guy here, all right, so we have C4, we have C3, that's good. Up here we have equation 4, we have C1 now. We don't have C2, so we're going to solve C2 with that, and then we should be able to go back and find those values when we plug them back into to these equations up here. We can solve some of those, solve CY, and we can find that. So we'll use these equations here to find CY, and then we'll go back to our equations of equilibrium to find that. Alright, so actual displacements here. From equation 4, we get CY over 6 is L over 2 cubed. This is our x value. Plus, here's one of our constants. This guy up here, C1, is going to be PL squared over 8 minus CYL squared over 2 times our x position, L over 2. And then the other equation works out to be CY over 6 times L over 2 cubed minus P over 6 L over 2 cubed plus PL over 4 L over 2 squared plus CYL squared over 2 times L over 2 plus CYL cubed over 3 minus PL cubed over 12. So that was our C4. This was C3. Those guys come through. So we expand those out. What do we get? We get CYL cubed over, that becomes 8, 48, plus PL cubed over 16, that term, minus CYL cubed over 4 equals CY L cubed becomes an 8 down there, so it becomes a 48 minus PL cubed. That becomes an 8 again, 48 plus PL cubed over, that becomes a 416 plus, what do we get here? We get negative CYL cubed over 4 plus CYL cubed over 3, so it'll be the same terms, minus PL cubed over 12. Alright, there's that crazy monster. What do we get here? So we get a bunch of PL cubed terms, we get a bunch of CYL cubed terms, and I think we'll just work on comparing those two together. So adding these two together here, I need to multiply this by 12, so I get negative 11 CYL cubed over 48 plus PL cubed over 16. Maybe we'll make that 3 over 48 there, because we got 48s over here, equals CYL cubed over 48. What else do I have here? So as I add that, minus, it's going to be 12, minus 12 CYL cubed plus 16 CYL cubed from this guy. Alright, that's it there. My 48s, I get, let's see, I get 3, negative 2. Okay, so let's just do it here. Negative 1 plus 3 minus 4 over 48 times PL cubed. Alright, so what do I get there? I get, let's simplify these down. So this is 1, negative 11 plus 5 48ths CYL cubed. So it's negative 11 48ths CYL cubed. On the other side, so my 3PL cubed over 48. So I'm trying to solve for CY here. So I got that one. I get negative 1 plus 2, negative 2 minus 2 48ths PL cubed. So I slide that one over. Let me keep CY on the right side here. So we get 16 48ths CYL cubed. That's nice. It gives me 1/3. Add 2 48ths to both sides for that one. I get 5 48ths PL cubed. Multiply both sides by 48. CY divided by L cubed. CY equals 5/16 P. So there's one of my reactions I found using all of those boundary conditions, continuity equations, etc. So there's that one. Whew, that was a lot of work. Now what am I going to do with that guy? Well, I found a CY, so I need to go back up here. There we go. So our equations of equilibrium back here. Now I can fill CY in here. So we'll solve A, Y, and BY as a result. So as I look at that, what do I get? My moments, I'm going to do first, right? So I'll be able to solve BY directly, because I have CY now. And then I can go back to my forces in that bit. So what was that? It was going to be 5/16 P. I might just slide over here rather than copying these down. It's a little hard to scroll back and forth. CY is 5/16 P. So what is this going to work out to be? So we get, I'm solving for B, so I get PL over 2 plus 3L over 2 times P. Move those two to the left side. Minus 2L times 5/16 P equals by times L. So if I divide by L, I get that guy to go away, this guy to go away, this guy to go away, that guy to go away. And what do I end up with? By looks like we'll be at 16ths. I guess we could go to 8ths if I wanted to. I'll do 8p plus, I'm going to multiply that by 8, 24p minus 10p over 16. I just wrote equals by on both sides. So what do I get? I get 14, 22, 22/16, or 8/11, or 11/8, excuse me. Now filling these guys up into here. So we get AY, just rewriting this equation, is 2p minus by minus cy, 2p minus 5/16 p minus 22/16 p. So AY equals that 27th 5/16 p. So there we go. There's all our values. Whew, that was a lot of work. Where are we at here? So we did our integration. We solved using boundary conditions and continuity. Went back to those equations of equilibrium. Now we just need to draw the shear and bending moment diagrams. Alright, so we had 5/16, 11/8, and 5/16. So what do we have? Ooh, there we go. Down here. Alright, so here's our shear. So at A, we go up 5/16 P. At L over 2, we go down. And what is that going to be? That's going to be negative 11/16. This is at L over 2. It's going to continue on until we get to L. And we came up. How much did we come up at B? Sorry, I forgot that. Scrolling. I'm not making you 2/6. 11/8. 11/8 gets us more than 1, so it's going to get us up to 11. So like that. 22. So it's going to get us 11/16 over here. It's at L. And then at L over 2, we come down. It's going to be negative 5/16 P. Coming over here, then we come back up 5/16 there, right? This is at, this is 3L over 2. This is 2L. Alright, here's our crazy shear diagram. Alrighty, and now our moment diagram. So I might need a little bit of room here. Shrink that down a little bit. I'll zoom back in a moment. So we're going to start out no moment here. What do we get? We're going to do L over 2. So we get 5/32 LP as our peak here. At that point. And then we're going to change. We drop. Our slope is going to go higher. And now we go negative 11/16 times L over 2. So what is that? Negative 11/32. It's going to be our change. So it's going to be negative 6 LP at that point. Maybe drew it a little too large. And we have positive 11/16. And I've got this a little spread out more than I need to. And that should get us back to that same point. and then that bit stretches out here. So there's our moment here for that bit. Alright, so a little convoluted there, but we got there, and we should be something that looks kind of symmetric about this point. I got a little crazy, but you get the idea. This was at L over 2, this is at L over 2, 3L over 2, this is at 2L. Alright, so a little crazy problem here, pretty in-depth. So again, we started with the elastic curve that helped us figure some things out. Free body diagram was the equations of equilibrium, which we came back to at the end once we used continuity and boundary conditions and our elastic curve to find our deflections, and then we came back and found what that looks like. So thanks for sticking with me. Hopefully this was helpful. It's going to be one of the homeworks, so all the best in your homework work, and as always, reach out if you have any questions or problems. Thanks.